Hi everyone and welcome back. We are continuing with chapter 4 this week. So this week we'll be going over 4.3, 4.4, and 4.5. So last week we only did the two sections, and as you saw it was a lot. This week we're going to finish off, and these sections are not quite as heavy. So hopefully everything makes sense to you and you become experts on this. So in 4.3, we're going to be talking about reaction stoichiometry. And with that, we're going to explain the concept of stoichiometry as it pertains to chemical reactions. We're going to use balanced chemical equations to derive stoichiometric factors relating amounts of reactants and products, and perform stoichiometric calculations involving mass, moles, and solution molarity. So just to kind of talk a little bit about stoichiometry itself, we need balanced chemical equations to do this because it gives us a lot of information in a really small amount of space. It tells us the identities of our reactants and our products, and then it has coefficients that gives us relative numbers of these chemical species, and the relationships between our reactants and products is what stoichiometry actually is. So don't let the name stoichiometry or the word scare you. It's just a fancy way of saying math and chemistry. Don't let that scare you either. Chemistry and math are buddies, and chemistry gives math meaning. Sorry, math majors. So before we start getting into chemical reaction stoichiometry, let's think about cooking. For instance, let's say a recipe for some really bland pancakes says you need a cup of pancake mix, 3/4 a cup of milk, and 1 egg. I guess that's not super bland, but I like to usually add maybe a little vanilla, even a twist of lemon. Doctor those suckers up. Anyway, if we were to make this into an equation, we could say 1 cup of milk plus 3/4 cup of milk, 1 cup of mix plus 3/4 cup of milk plus 1 egg react to form 8 pancakes. So I know that if I have a cup of mix, 3/4 a cup of milk, and 1 egg, I can make 8 pancakes. But let's say I need more than 8 pancakes. I need 2 dozen, aka 24 pancakes. So we need to then increase the amount of ingredients proportionally according to the amounts given in the recipe. So if I want 24 pancakes, I multiplied this 8 times 3. So that would mean I need 3 eggs, 9/4 cups of milk, and 3 cups of mix. And if we want to look at the units here, we can say we have 24 pancakes, and we know by looking at this that 1 egg makes 8 pancakes, so we can make that into a conversion factor. We could say there's, like we did here, 1 egg over 8 pancakes, and we do it with pancakes on the bottom so they cancel out, and we're left with eggs as our units, and we see 3 eggs. And we can do this for all 3 of the ingredients we need. This is really similar to a balanced chemical equation because it can tell you the amount of one reactant that we need to react with a given amount of another reactant, how much reactant you need to make a certain amount of product, how much product you can make from a certain amount of a reactant, how much of one product you make when you know the other amount of product, and all these other kinds of things. Okay? So these coefficients give us stoichiometric factors. Okay, and that's just the numbers in front of each chemical compound. So here's an example. N2, nitrogen gas, reacting with 3 hydrogen gas to make 2 ammonias. So if we look at this, we see that we need 1 nitrogen for every 3 hydrogen for every 2 ammonia. So we could say that we make 2 ammonia for every 3 hydrogen, Okay, right here on the bottom. We could also, instead of saying, this many molecules, we could say it's dozens. We could say 2 dozen molecules for every 3 dozen hydrogen molecules. It's the same ratio. And with that, we can still say 2 moles of ammonia for every 3 moles of hydrogen. And this ratio here, using moles, is definitely the way to go overall, because this is how we actually can do calculations. Okay? But you can relate the nitrogen to ammonia. We could have 1 mole of N2 for every 2 moles of NH3. We could also write that as 2 moles of NH3 for every 1 mole of nitrogen. We can relate everything here. We can say 1 mole of N2 per 3 moles of H2. 3 moles of H2 per 1 mole of N2. And then we did ammonia and hydrogen already, or we could write that as 3 moles of H2 per 2 moles of NH3. And how you write your factor all depends on what you're trying to calculate and cancel. That determines what goes on top and what goes on bottom. So here's another example. How many moles of iodine are required to react with 0.429 moles of aluminum, according to this equation? Okay, so we are given 2 aluminum plus 3 iodine gives us 2 aluminum iodide. One thing I want to give you a warning for your exam. Exam warning. Since that's coming up, you may be given something like this. Okay, or like some stuff we're going to go over later. But it may not be balanced. So you would need to balance it first before you can do anything. I'm known for doing things like that. Always check the balance. Okay, so always make sure your equation is balanced. And let's do this to see who actually listens to my lectures. On your midterm, there'll be a little spot towards the bottom where I might ask I might ask for a joke or something kind of silly. Usually there's 1 or 2 extra credit fill in the blanks I give. In either one of them, write the code word. And the code word is balance. And I will give you an extra 5 points on top of the already extra credit. So on your exam again, in one of the extra credit spaces, just somewhere in it, you can still answer the extra credit, whatever it asks, but just make sure to add the word balance somewhere, and I'll give you an extra 5 points. Cool? Cool. And no, I didn't write it on the slide. I probably should, actually, All right, so on exam, in one of the extra credit spaces, doesn't matter which, give your answer plus this code word balance for an extra 5 points. All right. And don't tell your friends who don't listen to the lectures, Because why should they get the reward, right? All right. So before we get into the reaction, they're solving this problem, here's some pictures of the actual reaction of aluminum and iodine. It's kind of a cool reaction, produces this really pretty and also dangerous cloud of purple smoke. So one of our first steps to do, so they broke things down into step by step, which is fine. We can do it all in one fell swoop as well. Actually, this is only a one-step process anyway. Because we're given moles of aluminum, we need to get moles of iodine. That's what we're asked for. Right? Because we want to know how many moles of iodine are required to react with 0.429 moles of aluminum, according to the chemical reaction. So just to kind of rewrite the reaction so you can see it here. I should probably do my eyes like that. Okay. So we are given 0.429 moles of aluminum. And based on our reaction, I see 3 and 2. 3 in front of the iodine, 2 in front of aluminum. So I know that I have 3 moles of iodine for every 2 moles of aluminum. And I need aluminum to go away. So that's why we have it in the bottom here. And we're ending with moles of iodine. So we plug that into our calculator and we get 0.644 moles of iodine. Now you can also be given ones where there's more steps. So in this example, for some reason they didn't actually write the question here. We want how many carbon dioxide molecules. So we want the number of CO2 molecules that are produced when 0.75 moles of propane, moles of propane is combusted according to this reaction. We're told C3H8 plus 5O2 yields 3CO2. Let me rewrite that where it's not in the way. C3H8 plus 5O2 makes 3CO2 plus 4H2O. Okay, so we are given 0.75 moles of propane, which is C3H8. And we want to know how many molecules of carbon dioxide are made. So we can use our balanced reaction. Using the stoichiometry, we can go from moles of propane to moles of carbon dioxide. From using the stoichiometric factor, we see that there are 3 moles of CO2 for every 1 mole of propane. And then we can go from moles to molecules using our good old friend Avogadro's number. And there's 6.022 times 10 to the 23rd molecules for every 1 mole. So all that's left to do is plug and chug. So let's make our little table here. We have 0.75 moles of propane. And we want to change that to moles of CO2 using our factor here. 3 moles of CO2 for every 1 mole of propane. We can see moles of propane would cancel right there. And now we want to go from moles to molecules. And there's 6.022 times 10 to the 23rd molecules for every 1 mole. In this case, this is CO2. We can see moles of CO2 cancel. And when you plug that into your calculator, you are left with 1.4 times 10 to the 24th CO2 molecules. Yay for stoichiometry! Now, these have been pretty straightforward, and honestly, in my opinion, stoichiometry is pretty straightforward. But the thing is, we don't have a way in the lab of measuring just moles, right? How do we measure amounts aside from, we can do volume, but the main way we measure amount is by taking mass. So we need to be able to go from grams of one thing to grams of another. And we need to do that using stoichiometry. So here's an example. It's a much easier way is to go through an example than to tell you about it. Okay, just checking something real quick. Okay, so we want to know how much sodium hydroxide would be required to produce 16 grams of the antacid milk of magnesia by this reaction. And here's another little warning. You may not be given the written reaction. You may have to write it yourself. Okay, you may have to figure it out on your own. I may just tell you the words. So you may just be given what's above, and then you have to write the reaction out and balance it and go from there. Okay? All right. So we're given grams of magnesium hydroxide. Okay? Now, I cannot just go straight from one mass to another mass. That doesn't work. I can't just go from grams of magnesium hydroxide to grams of sodium hydroxide. I first need to go from grams of A, whatever I'm starting with, to moles of A. Okay, so in this case, moles of magnesium hydroxide, using our friend molar mass. And from there, I can go from moles of one to moles of the other, using that stoichiometric factor. And then I can go from moles of B, in this case sodium hydroxide, to grams of it. So you have to calculate their molar masses as well. All right, so there's more steps involved, but this is how we actually do this in a lab. So we started with 16 grams of magnesium hydroxide. To change it to moles, we got to calculate its molar mass, which we can calculate to be 58.3 grams per mole. So there's 1 mole of it per 58.3 grams. We need grams to cancel, so that goes on bottom, moles on top. Using our stoichiometric factor from the balanced equation that was given to us, there's 2 moles of sodium hydroxide per 1 mole of magnesium hydroxide. So magnesium hydroxide cancels, that's on the bottom. Sodium hydroxide's on the top. Now we need to go from moles of sodium hydroxide to grams of it. Oops. So to do that, we have to use the molar mass. 40 grams of sodium hydroxide for every 1 mole. Our moles cancel. We're left with 22 grams of sodium hydroxide. Okay, so this is a very common type of calculation that you will probably be doing kind of over and over and over in this class. So these are just a couple examples of stoichiometry calculations. Sometimes you have to do them using volume, okay, and concentration. But all of these come down to needing to use those stoichiometric factors used in the balanced equation. And your book gives you this really nice flow chart to do this. So you find with what you're given. So let's say you're given a volume of some solution and you're given its concentration. Okay, so when you have a volume and a molarity, then you can go straight to moles. And then you can go from moles of A to moles of the other. And then use molarity again to go to volume. Okay, if you're given number of particles, Avogadro's number gets you to moles. If you're given a volume of a pure substance, use density to get mass, and then use mass to get to molar mass, use molar mass to get to moles. So all of these different ways all come down to using that stoichiometric factor. And you can see how you can also interconvert between these different things. Maybe you need to start from volume of A and end at particles of B. So this table might be very helpful to use maybe on your exam or something. Have it out, print it out, have it next to you, have it open in another tab or something. Okay. Airbags, your book talks about how they're an example of a chemical reaction because they use, it's a reaction, it's a decomposition of sodium azide, NaN3. So what ends up happening is there's a specific amount of it in the airbag, and if you're in a collision when the sensors detect it, it passes an electrical current through it, which causes it to decompose into nitrogen gas and sodium metal. And that nitrogen gas ends up inflating the airbag, which I got to experience what that feels like earlier this year in January 2020. Pay attention to the road, kids. I learned that the hard way. So did my insurance rates.